let's look at proving the cosine rule. So what we have is a scalene triangle, which in other words is a triangle where all three sides are different in length, and we've got vertices of capital A, capital B, capital C, and then the side lengths opposite are labeled as lowercase c, lowercase a, and lowercase b, corresponding to each of the vertices. So the first thing we can do is we can draw in the perpendicular height of this triangle in the following way. So starting at the vertex B, drawing a dotted line going down, we have the perpendicular height h of this triangle. And so since this is the perpendicular height, we can mark on a right angle symbol here and a right angle symbol here to indicate that this line here and the line AC are both perpendicular to each other. And so we've got two right angled triangles within this scalene triangle. So labeling the point where the perpendicular height and the side AC meet, let's call that capital D. Then we can also consider the base length of the triangle ABD. So the base length of the triangle ABD we're going to label as lowercase x. So this full length here we're going to label as lowercase x. And so if the length from A to C is lowercase b, then the length from D to C is going to be that full length minus the length from A to D. In other words, as an expression, we would have that D to C is equal to B minus x. Now, looking at the cosine rule, we have a squared term for A, we have a squared term for B, and we have a squared term for C. This looks very similar to Pythagoras' theorem. And in fact, we use Pythagoras' theorem to obtain squared terms from this triangle and the scenario that we have here. And so the first thing that should come to mind is, how can we get these terms? Well, let's use Pythagoras' theorem since we have two right angled triangles. In triangle BDC to start off with, so that's the triangle that's right angled on the right here, we have, using Pythagoras' theorem, we get a squared, which is the hypotenuse, which equals to h squared, which is this side length here of the triangle BDC, plus b minus x all squared, which is the other side length of the triangle BDC. And now expanding the brackets on the right hand side, we get the following equation. So a squared equals to h squared. Now if we expand this, we get plus b squared minus 2bx plus x squared. You might want to take a moment to convince yourself that b minus x all squared leads us to these three terms. And so we begin to see that this expression is starting to look quite similar to the cosine rule that we have here. There are a few terms that are slightly different, such as h squared, x squared, and the x within minus 2bx. However, we have some similar parts such as a squared and b squared. We also apply Pythagoras' theorem in triangle ABD, then we get the following equation. So we have the hypotenuse squared, which is c squared, which equals to the base of this triangle ABD, which is x, and we square that, plus the other side length or the perpendicular height of this triangle, which is h, and so we square that. And so we see that both this first equation that starred here and this second equation that starred here both have h squared in common. If we rearrange this equation here for h squared, in other words, make h squared the subject, then substitute that into this equation, we can get rid of the h squared and further get closer to proving the cosine rule here. We end up with h squared equals to c squared minus x squared. We label this equation as equation 1, and we label this equation as equation 2. Then the next step involves substituting equation 1 into equation 2. So this would result in the following. So looking at equation 2, we have a squared, which equals to, and now instead of writing h squared, we're going to write c squared minus x squared, since we're substituting equation 1 into equation 2. So we have c squared minus x squared, which is our substitution, and so we've written that in brackets, plus b squared minus 2bx plus x squared. So in this case, the brackets don't make a difference, so we can get rid of those, and so we have a squared equals to c squared minus x squared plus b squared minus 2bx plus x squared. And now we see that minus x squared and plus x squared cancel, and so we're left with a squared equals to c squared plus b squared minus 2bx. So again, comparing what we have so far with the cosine rule, we see that we've got a squared, we've got b squared, we've got c squared, and we've almost got minus 2bc cos a. Instead, we've got minus 2bx. Let's rearrange this so that the terms are in order of the cosine rule. So we have a squared equals to b squared plus c squared minus 2bx. Instead of having x, we need c multiplied by cos a. And so since we have cos a, we see that in this triangle, we have a right angled triangle on the left, where the vertex here is labeled a, and so we can work out cos a to obtain an expression for x, which we can then substitute in. And so in triangle ABD, we have cos a equals to, so whenever we take cos of an angle, we look at the adjacent side over the hypotenuse. And we can only use trigonometry or SOHCAHTOA when we have right angled triangles. Since we have a right angled triangle here for ABD, we can use this. So cos A is equal to the adjacent side. The adjacent side is labeled as x over the hypotenuse. The hypotenuse in this case is the side that's opposite the right angle, and so that would be C. So we have cos A equals to x over C. Multiply both sides by C, we end up with C multiplied by cos A, which equals to x. So finally, if we substitute c cos a equals to x into this equation here, a squared equals b squared plus c squared minus 2bx, we get that a squared equals to b squared plus c squared minus 2b, and instead of writing x, we're now going to write c cos a. And we see that this indeed is the cosine rule here. So we've proved the cosine rule.